This video introduces FloEFD for Solid Edge, Mintagraphic's latest addition to its CAD-Embedded general-purpose CFD family of products. FloEFD combines all simulation steps, starting from directly using your Solid Edge CAD data for model preparation to mesh generation, solving, and results visualization, all in one easy-to-use package. Let's start with an example to see how FloEFD for Solid Edge works. And for this, we will use a model that was supplied courtesy of Cullimore Racing, which is a participant in the Green Power Electric Car Challenge. Green Power provides an opportunity for students of various ages to design an electric car and compete on the racetrack. Solid Edge from Siemens, which is a Green Power sponsor, is the CAD tool that the students use in the challenge to create their designs. So let's take a look at one of the vehicles from Cullimore. Here we are in Solid Edge. You will notice that because of the FloEFD add-in, there are a few additions to the interface, like the Flow Analysis tab for the command ribbon, the FloEFD tab for its docking window, which is also available from the drop-down menu. What you will notice as we set up the flow problem and ultimately look at the results is that FloEFD ends up feeling like an extension of your already familiar Solid Edge environment. And one of the keys to that is being able to work directly with your native Solid Edge model. So here we have a simple assembly made up of the car plus the second part I added to represent the ground. In this case, the designer would like to run an external aerodynamic analysis to understand the forces acting on the vehicle and ideally modify the design to reduce the drag force. So let's see how we would set that up. A common way of setting up a FloEFD analysis is to step through the wizard, which guides you through defining various inputs you will need for the problem. The first screen of the wizard lets you name your project, which I'll do now. One of the benefits of FloEFD is being able to test various cases within the same Solid Edge assembly to compare your results and arrive at the best design. So our first case I'll just name Test 1. Next, I'll choose a unit system. I'll go with a standard inch-pound-second system, although I'll change my velocity unit to be miles per hour, as that would be a more convenient input for this type of problem. Next, we start to define the analysis a bit more. To begin with, we choose whether it is an internal or external flow problem. Certainly, FloEFD can be used for a very wide range of applications, many of which are internal flows, like manifolds, ducts, pumps, electronics enclosures, etc. And FloEFD would be considering the empty internal spaces of the solid model as the flow regions that need to be meshed and analyzed. In our case, however, we will be modeling the space around the outside of the solid model, so this would be an external case. For this example, the other physical features don't apply, so we'll move on. Next, we will choose our fluid for the study, which of course will be air, and that is located in the gases group. We'll choose air and move along. Next, we could input some default wall conditions if applicable. In our case, the defaults are fine, so we'll move on. And lastly, we'll define our initial and ambient conditions. In our problem, we will set up the model similarly to how you would test a physical model in a wind tunnel, in that our car is stationary and the air is moving towards the car at the correct relative velocity. So based on how this model is built in Solid Edge, the x-axis points forward in the driving direction. So our free stream air needs to be flowing in the negative x direction. So for this type of small electric car, let's test this case at 30 miles per hour. And we can finish up. As it finishes, you'll see that a new project is created in the FloEFD tree named Test 1. There are a few things left to do to finish setting up the problem. First, we can see that a large box has been created around the solid. This represents the air volume. However, it is larger than it needs to be, including that it extends below the part that I made to represent the ground. So I'm going to click on the computational domain icon in the FloEFD tree and start to drag the sides of the box to be more in line with the size that I want. I'll move my view around a bit as I adjust the domain size. You can also input a value directly for a location if you'd like. Another aspect of FloEFD to notice is that the user does not need to explicitly create a solid of the fluid region, which is common with other CFD codes. FloEFD will recognize the shape of the space around the vehicle as air and exclude the shape of the solid itself. Another input we should give this problem would be a boundary condition for the ground surface. If the ambient air velocity is 30 miles per hour in the negative x direction, then we should also have the ground surface sliding at the same speed and in the same direction. To assign this, we will go to the Boundary Conditions branch of the tree and right-click and select Insert Boundary Condition. To select the face to apply the boundary condition to, you can just select it using a typical solid edge selection approach of right-clicking and selecting the appropriate face. Or I could just select the part itself and then apply a filter to remove faces that are outside of the domain. Then I would choose a wall type boundary condition, select the wall motion option, and then give it a velocity of -30 miles per hour. We've basically assigned all of the inputs we need to run the analysis. At this point in the setup, we can identify some overall outputs of interest that we would like to get from the results. We use goals in FloEFD to identify these outputs. So one of our main values of interest in this case is the drag force. To extract this, I will right-click on Goals and choose Insert Surface Goals. I'll select the part of the car and then scroll down and choose the parameter for force in the X direction. This goal will also be used as a convergence criterion during the run. Lastly, we'll take a look at our mesh settings. One of the core strengths of FloEFD, which overcomes a long-standing bottleneck in the CFD process, is its meshing approach. We'll start by looking at the global mesh settings. The more common option is to use the automatic approach, which uses a slider bar to control the mesh fidelity. You can take a look at the base mesh from this GUI, with these being the starting cells that the mesher will use, while the cells near the solid bodies will ultimately be refined to higher levels based on criteria from the auto mesher. Additionally, you can add some local meshing if you would like to further control the mesh. And a powerful and convenient option, especially for this type of problem, is to make use of solution adaptive refinement, in which the mesh will be modified during the run to better capture regions of higher flow gradients. So at this point, we are ready to run the analysis to obtain the CFD results. Once the run is completed, we can start to take a look at the results in Solid Edge. First, let's take a quick look at the mesh. I'll start with a cut plot, and I'll choose to display the velocity field as well as the mesh along the center plane. You can see the style of mesh that is created, and you can see that we have cells of various refinement levels due to either the need to capture the geometry or based on the solution. For example, you can see more cells around the top of the vehicle and wake region as it refined the cells to better resolve the flow field. Now, instead of viewing the mesh, I'll change the plot to include vectors. Or for this case, maybe an even better option is to show streamlines, which helps us further understand the flow structures around the car. And you should note that we are viewing these CFD results directly with your original Solid Edge model. Next, let's say that instead of just looking at the solution on a plane, we'd like to add a surface plot of the vehicle. This provides a more three-dimensional understanding of the flow around the car. And of course, I can move the cut plot to any location I'd like, or just hit the play option and let it sweep back and forth across the model. Another valuable way of viewing the solution for these types of problems is to plot flow trajectories. These are essentially the flow of massless particles and provide a nice view of the flow field as it passes over the car. There are many viewing options for these trajectories, like a static view of bands like I am showing here, or I could change these over to be animated arrows like so. So far, we have shown various ways of visualizing the flow, but let's say that the engineer would like to extract some quantitative values. We had set up a goal prior to the run for the overall drag force acting on the car, so this information could be accessed easily now from the goal plots branch of the results tree. Or instead, perhaps the designer would like to look at the force acting on a specific part. Even though we had not set up a goal prior to the run, we can still easily get this data afterwards by using surface parameters. Let's say that we want to know the forces acting on the bar at the top of the vehicle. We can just select the part directly and either display the integrated results in the graphics area or have this information sent to Excel. Just one more convenience for the engineer using FloEFD. Now, to this point, we have looked at generally the overall procedure for running a FloEFD analysis, from setting up the problem through the wizard and the input portion of the tree to examining the results in the Solid Edge interface. A final consideration would be to understand how to explore different design cases, which, after all, is at the heart of engineering, testing different ideas to arrive at the best design. From here, we can clone the project, which would set up a new case in our Solid Edge assembly that already is set up the same way as this current case. In our new project, we could change a flow parameter like the speed of the air, or perhaps more interestingly, make a design change to the vehicle, which is easy because we have been using the native Solid Edge model for the analysis. Or even further, instead of just one case, we could create a parametric study. In this utility, we can set up the parameters we would like to vary as a what-if scenario or even as a design of experiment study to arrive at an optimum design. Through this video, you have seen how Mentor Graphics now brings a fully CAD-embedded CFD solution to the Solid Edge community. With FloEFD, design engineers can now conduct upfront concurrent CFD analyses using their familiar Solid Edge interface directly on their Solid Edge model. Design better, faster with FloEFD for Solid Edge.